All right. Hey, everybody. I am narrating over the video that I already made and posted that seemed to have no audio. So the writing is a totally disembodied hand, and I'm just watching what I wrote the first time and trying to comment so that the video makes sense. So this is the first video in 7b. And it's about what's called the spectral theorem. And the spectral theorem reads differently depending on whether or not you're over the complex field or the real field. So today's self-contained discussion in 7b is about what's called the complex spectral theorem. So here I'm just writing it out. We're jumping straight in. This is the statement of the theorem. So we start with a complex finite dimensional inner product space. And you got an operator T on that inner product space V. Now, the beauty of this spectral theorem is that it tells us exactly what the normal operators are. So T is normal if and only if, this is remarkable, if and only if you can find a basis for V that is orthonormal and makes T's matrix representation diagonal. So T is normal if and only if there exists an orthonormal basis with respect to which M of T is diagonal. So that's the theorem, and this is just really nice. It says, oh yeah, certainly some operators are diagonalizable, but that just means there exists a basis of eigenvectors. There's no reason to believe that basis of eigenvectors is orthonormal. Those eigenvectors might not be perpendicular to each other at all in general. It's the normal operators that guarantee us that orthonormal basis of eigenvectors. Anyway, it's if and only if, so the proof is in two directions, and the reverse direction is actually a little bit easier. So I think I remember earlier today writing this out that we started with the reverse direction. So let's see if we can prove this thing. Come on, Retzek, write proof. It's time. Let's prove this. What am I rambling about? We'll never know since there was no audio. I must be going on and on about something right now. I'm ready to prove it. Okay, here we go. That scroll was promising. Yes, proof. Okay, cool. So I think we're going to do the reverse direction first. So I think we're going to suppose that we have an orthonormal basis with respect to which M of T is diagonal. And that's a huge supposition right there. So it doesn't surprise me that we should be able to draw a fairly big conclusion from that supposition. So let's suppose E1 through En are an orthonormal basis for V. And furthermore, that they make T's matrix come out diagonal. So E1 through En are an ON basis. And with respect to that basis, M of T looks like this. Big old square matrix because it's V to V. And we got entries down the diagonal and then zeros everywhere else. So that's the supposition in the reverse direction. Kind of a monstrous supposition. Okay, well, this direction is pretty much done then, because we already know if you want to know the matrix for T star and the basis is orthonormal, then for free, all you have to do is the conjugate transpose. So the matrix for T star takes no work to build. You just do the conjugate transpose for that thing. So you just get those diagonal elements all conjugated. So complex conjugates. Remember, those entries could be complex numbers in this theorem. And then when you flip across the diagonal, all the zeros above it become zeros below it and vice versa. So it's still diagonal. And now you're done, because diagonal matrices commute. If A and B are diagonal square matrices, same size, then AB does equal BA. It's not true in general. Typically for matrices, AB and BA don't come out the same. But for diagonal matrices, they do. And that means that no matter what order you multiply in, T star or T star T comes out the same. And so here in this little parenthetical remark, I'm just indicating why, since diagonal matrices commute. So that direction's done. If it's already diagonal, then so is the matrix for T star. And therefore, T and T star commute. Okay. Now, the forward direction of the proof offers a little more intrigue. It's going to have us assuming that the operator T is normal, and then having to argue that there exists an orthonormal basis with respect to which T's matrix is diagonal. So here, the supposition seems a little more modest, and the conclusion we're trying to draw seems kind of huge. There exists an orthonormal basis. I mean, where are we going to get that? Well, it's not all bad. In a complex finite dimensional vector space, in a math 306 way, for sure there's a basis that makes the matrix upper triangular. We know this for sure from math 306. Once there's a basis that makes the matrix upper triangular, then you can do Gram-Schmidt to that basis, and you won't ruin that the matrix is upper triangular. So we know we have an orthonormal basis with respect to which T's matrix is upper triangular. That's where it stands. That's, I think we called that Schur's theorem maybe, back in chapter 6. Was it 6.38 maybe? Something like that. Schur's theorem is the one that says, well, if your inner product space is complex, finite dimensional, then you definitely have an orthonormal basis with respect to which the matrix is upper triangular. Okay, so this is me just writing that out right now. Certainly, yeah, after all those sentences, certainly there is an orthonormal basis E1 through En such that M of T turns out upper triangular. So that means some stuff down the diagonal, zeros below the diagonal, and then who knows what above the diagonal. So that's what we know. Okay, our job is to argue that that big asterisk of who knows what above the diagonal is actually all zeros. And the only thing we have to work with is that T is normal. So we're getting close to being in business here. Okay, so we want to argue that everything above the diagonal is 0. So maybe let's just focus, we're going to focus on the top row. Let's just think of the stuff in the top row above the diagonal, which is funny because I just boxed the first column. But the first column's relevant also. Think about where that column came from. Like, how do you build M of T? Well, you see what T does to the first basis vector, E1. And if that first column's like that, that means TE1 is just A11E1. So T's action on E1 is easy. In fact, E1's an eigenvector with eigenvalue A11. And in particular, the square of the norm of T acting on E1, well, that's just magnitude A1 1 squared. Okay, fine. But remember, in this direction of the proof, t is normal. So that means the square of the norm of t acting on E1 is the same as the square of the norm of t star acting on E1. Remember, our operators are normal if and only if TV and t star v have the same norm. Okay, cool, but think about what's t star acting on E1. Okay, well the matrix for t star would be the conjugate transpose of that matrix I just pointed at. And so the first column of t star's matrix is the first row of this matrix, but with everything conjugated. So we're going to box up that first row of the existing matrix, recognize that if we conjugate all those entries, then we have in our hands the first column of t star. So we're going to give the entries some names, A11, A12, all the way through A1n. Those with bars over them are the entries in the first column of t star. So t star acting on E1 is in fact A11 bar E1 plus A12 bar E2, etc. So now I'm just going to write that. So we're replacing t star E1 with the linear combination of the e's that it must be due to the first column of the matrix for t star. But that's great, because that's just a linear combination of some orthonormal stuff. So you can find the square of the norm of that, no problem. We already know how that works. We studied orthonormality already. So that's just magnitude A11 bar squared plus magnitude A12 bar squared, all the way out to magnitude A1n bar squared. That's how you do norms of linear combinations of orthonormal things. Okay, so look at what we got. So in the top line of this discussion, we see the norm of TE1 squared is just the thing, I think I underlined it in purple coming up here. It's just magnitude A11 squared. There it is. On the other hand, the norm of TE1 squared is all this stuff underlined here. Come on, do it, Retzik. Underline all that stuff. I know I did. There it is. So the double underlines have to match. They both equal norm TE1 squared. So that means all the stuff besides the first term in the big double underline, all this stuff in the orange brackets, that's 0, which means A12 through A1n are all 0. So that's what I'm writing right now. A12 through A1n must all be 0, i.e., the matrix for T really looks like this. Remember, where were those entries? They were up there in that first row of this matrix. So that's all zeros. Down below, because it always was. Star, still who knows, but we do know a little. At least that top row of asterisk is all zeros. That's what we just argued. Okay, sweet. So we're part of the way there. Our aim was to show all of asterisk was zeros, and we just showed the top row of asterisk was zeros. Awesome. Okay, well, the rest of this is just to do the same thing. now that we know the top row of asterisk is zeros, can we focus on what t does to E2? So from that matrix right there, t acting on E2 is nothing other than A22 E2. And the square of the norm of that is just A22 magnitude squared. Okay, but now it's just Groundhog Day. On the other hand, since t is normal, if you were interested in the norm of TE2 squared, you know that's the same as the norm of T star E2 squared. But think about the matrix for T star. It's the conjugate transpose of the one we just wrote down. So the entries of asterisk there in the second row, we conjugate them, and those become the entries below the diagonal in the matrix of T star. And then you can read off from that matrix for T star that T star of E2 must be 0 E1 plus A22 E2, no, A22 bar E2 plus A23 bar E3 plus dot 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 all the way through A2N bar En. So you're reading that off from the matrix for T star, given the matrix for T that we have cooking. The matrix for T star is not written on this page, but you are inferring what its columns look like based on the rows of the matrix of T. Anyway, that's a linear combination of some orthonormal stuff. And so again, its norm squared is easy to compute. And again, looking at the norm of TE2 in these two different ways, you see that this chunk of that bottom line must be 0, and therefore A23 all the way through A2N must be 0. So I guess I'm about to write that. Oh yeah, okay, all the underline business again. Oh yeah, now the double underlines match. Okay, so this stuff in orange, I'm sure I used orange again. I did. That must all be 0. So the upshot is the second row of asterisk is all zeros also. And if you do this n minus 1 times, you find out all the rows of asterisk are 0. In other words, the matrix for T is straight up diagonal. Not just upper triangular, diagonal. Goodness, what am I going on about? It's clear. Dang, these videos could be shorter. It seems like. Oh, there I go again, drawing all the different rows of asterisk. Okay. Yeah, it's not bad. They end up all 0. That's the main point. Okay, so this must be some sort of summarizing statement. So after n such arguments, and then I changed my mind in the middle of this sentence. I was like, n minus 1? I think asterisk only has n minus 1 rows. We find all entries above the diagonal, so all entries of asterisk are 0. Sweet. Okay, so that ends that direction of the proof. We've done both directions, so the whole thing's over. Complex spectral theorem in the books. A linear operator on a complex finite dimensional inner product space is normal if and only if its matrix is diagonal with respect to some orthonormal basis. In other words, there exists an orthonormal basis of eigenvectors of T. So that's nice. These normal operators are great. They're diagonalizable, and they're diagonalizable in this really excellent way where you have this basis of eigenvectors that are orthonormal. It's really fantastic. Structurally, it makes working with normal operators much, much easier. Okay, moving forward, looks like there's like 40 seconds left in this video. I'm probably talking about at this point, hey, what about the real spectral theorem? So what about the one where the scalar field is the field of real numbers? It's not quite this. It's not quite this. In fact, there are normal operators that don't even have a single real eigenvalue. So it can't be exactly this. And it's actually a little bit more delicate. This is one of those times where working with complex numbers is easier than working with reals. So that's a 2-day discussion, and that'll start tomorrow. See you next time. Bye.